NanoHub U, online instruction.
Welcome back to Unit 1 of our course. This is the 9th lecture. Now, in the last lecture, we discussed these energy levels of graphene. And what we were trying to do is, this is a two-dimensional problem because this graphene is a two-dimensional material. And you have this Kx and Ky, and the energy is a function of Kx and Ky. And what you want is those energy levels which are close to the Fermi energy. And what we discussed is how we could plot out a certain function, and wherever that function is small, those are the regions where the eigenvalues are close to the Fermi energy, and those are these dark spots. And these are what you call the valleys. And just looking at this picture, it would look like you have 6 valleys, but in practice, it's actually 2, not really 6. And why it's 2 and not 6? That needs this discussion, with what this lecture is about. We'll talk about how you construct a reciprocal lattice and thereby see why it's really not 6 valleys but 2. And this is, of course, a general principle that applies not just to graphene, but to all materials in general. Okay. Now, just to recap, the basic idea of a valley is something like this. That supposing you had a simple 1D problem. You had an EK relation looking like this. There's a Fermi energy somewhere here. And so what determines conduction is the energy levels around the Fermi energy. And so you'd say, okay, here we got one valley. This is where all the conduction takes place. Well, if you had an EK diagram that looks like this, you'd say there's 2 valleys. Now, what might be a little more confusing is if you had an EK relation that looks like this. In other words, kind of the inverse of this. Have a Fermi energy is here, and looking at it, you might think that there are 2 valleys, one here and one here, but actually it's really 1 valley. And one way to say it is, yeah, there's a half a valley here and a half a valley there. So overall it's 1. Another way of saying it is that, well, here what we are drawing is the first Bravais zone. But as you know, in principle, we could take a window anywhere. We could use a different Bravais zone. And this function is periodic, so you actually goes on like this. So instead of using this Bravais zone, I could have used a Bravais zone like this. And in that case, of course, there would obviously be 1 valley right in the middle. Okay? But if we want to use the conventional Bravais zone, that's this one, the red one, then we should think of it as 2 half valleys. Well, what I'll try to show you in this lecture is, in graphene we have something similar. What we need to do is construct this Bravais zone. Now, in simple 1D problems or simple rectangular lattices, constructing the Bravais zone was relatively straightforward. Whereas in graphene, you have to do it more formally. And that's what we'll be doing in this lecture. And when you do that, you'll find that the Bravais zone looks something like this. You see? And now you can kind of see why the 6 valleys became 2. Well, it's because this valley, you only get 1/3 of it within the Bravais zone. Similarly, you get only 1/3 here and 1/3 there. So overall, it's like 6 1/3 valleys. Or there may be ways of choosing your Bravais zone or moving it around so that you get 2 full valleys. But in the conventional Bravais zone, at least, you'll get 6 1/3 valleys. Okay? So let me explain then how that Bravais zone is constructed. So for that, you first start from the real lattice and construct the reciprocal lattice from it. But before we talk about graphene, let's see how you do it if you had a simple rectangular lattice. Because in this case, you don't really need the formal method, but we'll do it the formal way. That way, you'll have it for using it for graphene later. Okay. Now, the first thing is, this is a rectangular lattice, and every point on this lattice can be written as a linear combination of 2 what are called basis vectors. Now, this is a little different from the basis functions that we talked about earlier in this course. Right? Here we are talking about basis vectors, and this is a two-dimensional vector which can be written in terms of the two basis functions, by two basis vectors. By contrast, the basis functions are kind of like is a much higher dimensional space, which is why you need many basis functions to represent your function in that context. Whereas here, we're just talking about any two-dimensional vector on this plane that you're trying to write down, and you could write it as a linear combination of this one and this one on this lattice. Okay? So this A1 and A2. What's A1? It's this vector in the x direction, A2, that vector in the y direction. Now, the way you construct a reciprocal lattice is, you first write down the basis vectors for the reciprocal lattice. That is, the reciprocal lattice is also rectangular in this case, and it's all the points here can be written as linear combinations of two basis vectors. One of them in the x direction, 2 pi over a, another the y direction, 2 pi over b. Now, the defining relation though between the basis vectors in reciprocal space and the basis vectors in real space, the defining relation is this one, that small a1 should be orthogonal or perpendicular to big A2, and small a2 big perpendicular to this big A1. Because when you know two things are perpendicular, their dot product is 0. So first thing is that this one here is perpendicular to that, and this one here is perpendicular to that. Next point is that if I take the dot product of this one and this one, the ones that are not perpendicular, then I'll get a non-zero number, and that should be 2 pi. Now, we didn't quite need this general prescription to write things down in the rectangular case, because in the rectangular case, it's basically simple. This was A, that's 2 pi over A. This is B, that's 2 pi over B. But in non-rectangular cases, it isn't as straightforward. And there, we need to follow this formal prescription of how, given small a1 and a2, you can find big A1 and big A2. And once you have big A1 and big A2, you can construct this lattice by taking linear combinations of them. Okay. Now, why is this important? Well, as long as these relations are satisfied, what you can show is that if I take any reciprocal lattice vector, capital K, and dot it with a vector in this real space, the answer will always be a multiple of 2 pi. Why is that? Well, take the dot product of this with that. Now, small a1 dot capital A1 gives you 2 pi. So that's this 2 pi small m capital M. That's the. Now, when you take ma1 dot it with the last one, you get 0. Why? Because a1 dot a2 is 0. You take the a2, dot it with the a1, again you get 0. And then you take the a2 and dot it with the a2, that's how you get the second term, the 2 pi. So the point is, you could have any integers capital M and capital N, any integer small m and small n, but if I take a dot product of a vector in this space with a vector in that one, the answer will be a multiple of 2 pi. Why is that important? Well, what it means is, when I write down a wave function, as you know, when we're describing the dispersion relations, when we're obtaining the dispersion relations, we said that in a periodic solid, you can write wave functions in the form of plane waves, e to the power I k dot r. And the point is that if I add a reciprocal lattice vector capital K to that k, makes no difference, it's the same function. So when you are classifying your states in terms of this small k, the point is any k is exactly equivalent to a different k which differs from it by a reciprocal lattice vector. And so if someone has a solution with some k and another person has a solution with small k plus capital K, the point is they are really the same solution. They shouldn't count as two separate solutions. So what that means is that in this k space, when we are trying to classify our solutions, we are looking at how many solutions we have, you should only look within a Brillouin zone, a region which is like around that point obtained by taking half these distances. So it's like you bisect all of these and get this region here. And the idea is that if you had another point K out there, there's always an equivalent point inside, which is equivalent, which means you don't need to look for a solution corresponding to the red X. It's really covered by the blue one, because they differ by a reciprocal lattice vector that much. So this is this idea of the Brillouin zone, the region, the domain in K space where you need to look at your eigenvalues. Anything outside basically is equivalent to something inside it. Okay. So we'll now use this general principle to construct the reciprocal lattice for graphene. Graphene, as you know, has this hexagonal thing, and what we have shown here is like one unit cell connected to 2 unit cells on this side, 2 unit cells on that side. And as you know, you're supposed to think of the red and the blue as one unit. Okay? Now, first question is, what are the basis vectors? Well, the basis vectors are obtained by taking this unit cell, let's say, connecting it to that one. So you can draw it between the red and the red, or the blue and the blue, same thing, same vector. So that's one basis vector. This is another basis vector. And any location on this entire lattice can be written as a number times A1 plus another, an integer times A1 and an integer times A2. Okay? So those are the two basis vectors here. Well, next question is, how would you write them down in terms of your X and Y coordinates? Well, the A1 has an X component which is that much, which is what we had labeled A, that's like half of that distance. And it has a Y component of that much, which is half of this. So you have AX plus BY. A2 is again same X component, but the negative Y component. So it's AX minus BY. And you'll see in a minute why I'm writing this. For the Z direction, of course, this is a two-dimensional solid, so the Z direction is kind of irrelevant. But let's write down a basis vector in the Z direction as well, which I'll just write it as C. Now, question is, how do I write capital A1 and capital A2 so that I can construct the reciprocal lattice? And there's a very simple general solution to this here, and that is capital A1 is given by that expression. What you can show is, if A1 is given by that expression, then automatically it will ensure that A2.A1 is 0 and that A1.A1 is 2 pi. So those two basic relations will be satisfied if I write my capital A1 this way. How do I see that? Well, this basically says that capital A1 should be perpendicular to A2. And this, of course, ensures it. Why? Because capital A1 is the cross product of A2 and A3. And as you know, when you take the cross product of two vectors, the resulting vector is perpendicular to both of them. So I have automatically satisfied this. Well, look, what about small a1 dot a1 equals 2 pi? Well, that's easy to see. Dot this with small a1. Then you see the numerator becomes exactly the denominator, so cancels out, and you're left with 2 pi. So next step then is, take that expression, use these A1, A2, A3 and evaluate it. First thing is the numerator A2 cross A3. So you have to take the cross product of those two things. Now X cross Z is minus Y. So you get a minus AY. Y cross Z, that's plus X. So you get a minus BX. Now we need the denominator. So you have to take that quantity and dot it with A1. So when you take the dot product of two vectors, what you do is multiply their X components, multiply their Y components, add it up. So it's plus A times minus B, so that's minus AB, and plus B times minus A, that's again minus AB. So you add it up, you get minus 2AB. So now if you divide it, you'll get the expression for capital A1. is pi over A in the x direction plus pi over B in the y direction. Similarly, we can write down the other reciprocal lattice vector A2. It is A3 cross A1 divided by that times 2 pi. Similar algebra, if you work through it, you'll get something looking just like this, but with the second one with its sign reversed. So we now have the reciprocal lattice vectors. Now we can try constructing the reciprocal lattice itself. What it will look like is, you stand at the origin, draw A1, for example. So what's A1? It's pi over A in the x direction, pi over B in the y direction. And what I've plotted here, though, you'll notice I'm not plotting kx and ky, I'm plotting kx times A and ky times B. So for A1, kx times A is pi, and ky times B is also pi, and that's why that point looks like pi comma pi. So that's A1. What's A2? That's this vector. So A1 is that vector, A2 is that vector. And this vector is just like the other one, but it's pi comma minus pi. What other vectors, what other reciprocal lattice vectors can I construct from standing from here? Well, various linear combinations of A1 and A2. So if I add the two, then pi comma pi and pi comma minus pi, when I add them, I get 2 pi comma 0. So that's this vector. This is A1 plus A2. This is just the negative of that. Similarly, this is the negative of that. And this, again, negative of this is that. So that's how you can write all the nearest neighbor vectors. And you can have longer vectors, one going out there, for example. And you can construct the entire reciprocal lattice. What we need is just this immediate vicinity. Because, if you remember, the Brillouin zone is obtained by drawing, kind of taking half of each one. So, drawing perpendicular bisectors. So, when you do that, you see, you take this, bisect it, take that, bisect it, take that, bisect it. And that's how you get the first Brillouin zone. And this is exactly what I had drawn earlier. You can see, it looks like, this point is right in the middle of that region where you have the valley. And this is also exactly in the middle of the valley, each one, which is why none of the valleys are really complete. So when you look at this region, you only have this 1/3 of the valley there. That's the A. See? Similarly here, you have just 1/3 of a valley, B. But of course, what you could do mentally is, this point is equivalent to that point. Why? Because they are separated by a reciprocal lattice vector. If I add a reciprocal lattice vector to this, from here I can get there, which means all the states here are equivalent to states over there. So instead of having 1/3 of a valley here and 1/3 of a valley there, I could kind of put them around the same place. Similarly, I could take the C, this valley from here, and move it up there. Again, by translating with this vector. So then you see, instead of having 3 1/3 valleys, you'd have one full valley around here. Similarly, these three, the ones here, here, and here, they could also be combined into one full valley around here. So you could say, okay, I've got one full valley there and one full valley here. But bottom line, of course, is that at the end of the day, graphene has 2 valleys. And you can see it was a relatively mathematical argument. We had to go through this reciprocal lattice, construct things in Fourier space and so on. But the number of valleys has a very direct consequence in terms of measurable quantities, which people have done this, is when people look at ballistic conductors, ballistic graphene or ballistic this carbon nanotube, which is like graphene rolled up into like a straw. When people look at the ballistic conductance, as you know, usually the ballistic conductance is supposed to be like 12.5 kilo ohms roughly. Why 12.5? Well, the quantum of conductance is, this quantum of resistance is 25 kilo ohms. There are 2 spins in parallel. So 25 kilo ohms in parallel with 25 gives you 12.5 kilo ohms. That's the ballistic resistance usually. But when you measure it in graphene or in carbon nanotubes, what you get is more like 6 kilo ohms, half of that. Why? Well, because graphene not only has the 2 spins in parallel, but also has the 2 valleys in parallel. And the point to note is it's 2 valleys in parallel, not 6 valleys, it's 2. And the argument, of course, why it's 2 is what we just went through. But the point I was trying to make is, although the argument is fairly mathematical, it has a very direct, experimentally verifiable consequence, namely the ballistic conductance. Well, that brings us to the end of the things we wanted to talk about in this unit, and now it's time to sum up. Thank you.